All right, so let's look at some of the very common vector concepts. Okay, just to jog your mind. Okay, because we're dealing so much in 3D, and we're using so much involved. This vector is so much involved for the rest of the concepts, right? So what is a vector first of all? All right, yeah. As we learned, you draw. This is how I will draw a vector in basically a 3D space. Okay. So in 3D space, basically means you have a Cartesian coordinates x, y, z, okay. And then you draw the vector starting from somewhere, okay, and then you draw an arrow ends with an arrow. Okay. So you're labeled with that a and a b. So that basically means this is a vector a and a b. So this is called initial point, and this is called the termination, right? Terminal point. Okay. Yeah. And you label this vector as a, b. Okay. So this is also a class. I want you to get used to some of the notations, some of the way I write the symbols. Okay. So when I write a vector, I will write a vector like this. So AB, on the top of the AB, and then there is an arrow here. Okay, so it's like a half arrow here. So I indicate this is a vector AB here. Okay. So this is not necessarily the same way as all in the textbook or in some other references. If you look at the textbook, you will see that they use bold letter to indicate a vector. But I can write a bold. So this is the most efficient way for me to write letter here. Okay. Yeah. So that's called a vector AB at here. Okay. So before I really talk about the actual meaning of vector, so let me ask you a question, okay, and see that how your understanding of vector is. Okay. So let's say I have an AB at here, right, and somewhere in a 3D space. So here's the thing. I'm not going to change this direction of AB, okay? And I'm not going to change the length of this AB. So all I'm going to do is I'm going to make an identical copy of the AB, and then I will move this vector from this original location, not changing the direction, right? So just basically move it parallel anywhere and then move it to somewhere else in the 3D space. So probably, let's say, I'll move it to over here. Okay. So make identical and move it to somewhere else. So let's say I call this if this is CD, so this is a CD vector here, right? Yeah. So here's my question. Are AB and CD the same vectors? All right, let's think about it. So how many of you think that they are not the same vectors? No, only one, two. Really? How many of you think they are the same vectors? Well, I guess well, more people think they are, but there are people who didn't raise their hands. So I take it if you didn't raise your hands, you probably are still maybe not quite sure, right? Or how many are unsure? Okay, yeah. Well, I don't know what the other think. So the answer is they are the same vector. Okay, they are the same vector. So why are they the same vector? So that really boils down to the definition of the vector now. So this is basically what I wanted to remind you at here. So what's the definition, right? Okay. The formal definition of vector basically if you want to call a vector, then you have to define two components. One is direction. The other is the magnitude or length. Okay, so these two elements are what defines a vector. Okay, so direction and the magnitude or length. They define actual vector. So in a mathematical way to write this one here. So when you're talking about a vector, whatever vector it is, then you will see that you can always write the vector as its length time its direction. Okay, its length times the direction. That's what defines the vector at here. Okay, yeah. So back to this simple question at here. I have AB and I have a CD, right? As I mentioned, that the CD is an identical copy of AB, and without changing its direction, you just move it to a different location, right? So you look at AB, you look at the CD. They all point to the same direction. They all have the same length. So according to the definition at here, then they must be the same vector. So that actually brings down to a simple sentence for vector. Basically mean vector is free. Okay, so you can move it anywhere, okay, without changing its direction and the length. Okay, so vector is free. Okay. Now coming back to the direction and the length, right? So how do I basically, let's say mathematically indicate the direction, mathematically indicate its length, right? Yeah. For the length, okay, for the length, it's easy. You have the vector at here, then we can use this symbol at here to indicate its length. All right, yeah. So all we do is we just put a absolute sign beside the vector at here, and we indicate a length. In some reference, more actually, if a mathematician teach you, and I believe they actually probably use this sign here. So basically double vertical lines, okay, to indicate this is the length of the vector here. So I just want to write one vertical line, so that's the length, okay? Yeah. So what about direction? Okay. Direction, the idea is simple. I mean, direction is basically, if you're given a vector, there's always a point into a direction. So the vector itself, AB. Okay, so the vector itself, AB, so naturally tells you the direction, basically. Okay, but we wanted to be a little more specific in terms of direction. So what do we do is, for direction, we use the so-called unit vector to indicate the direction of a vector. Okay, so we'll use the so-called unit vector for its direction. Okay. So now that basically brings the question, and then what is the unit vector, right? Let's use the AB vector as an example at here. Okay. So if we have AB at here, okay, which is a vector AB, okay, then unit vector is defined as we use this. So AB, let's write it clear, AB hat. So with a little inverted triangle, okay, AB hat. Okay, it's a sharp triangle kind of thing. AB hat equal to AB divided by this. Okay. So as you can see, the definition of a unit vector here, it's basically the original vector divided by its length, right? So that's unit vector. And the unit vector represents its length. And why is it called a unit vector? Yes?
Magnitude of 1.
That's right. Right? So if you look at its magnitude, it'll be 1. Okay? So that's why it's called a unit vector. Okay? Yeah. And what are the typical unit vectors so that we actually see quite a bit in mathematics in 3D? So in 3D, if I give you a Cartesian coordinates, okay. So x, y, z, right? So it's a Cartesian coordinates, and you have an x-axis, y-axis, and a z-axis, right? Yeah. And each one of the axes, the way what is called Cartesian coordinates is because each one of the axes are perpendicular to each other 90 degrees. Okay. So, and often in time, we represent the axis of these Cartesian coordinates using 3 unit vectors. So 1, 2, 3. Okay, and this first one here along the x-axis it is called I hat, and then this one here is called J hat, and this one here is called the K hat. Okay, these are the 3 most common thing notations, unit vectors that you will see in this class here. Okay, so I hat, J hat, and K hat. All right. Okay. So, and then let's look at basically a few concepts that are here. Okay, and also notations. Okay. Okay, so first of all, let's look at the length again. How do we calculate the length or magnitude? Okay. So we mentioned that, you know, in order to find a vector, you need a direction, and then you need a magnitude or length, right? So the direction can be obtained by doing this calculation, and then the length can be calculated by using this calculation here. Well, so that naturally basically brings us here. So how do I calculate basically what does this AB at here equal to, right? So what's the formula for this? Okay, yeah. So as you can see, how AB is formed are using the 2 dots at here, 2 points, A point and a B point. So you can calculate the magnitude using the so-called coordinates of A and B. Okay? Yeah. So for example, okay, if if the coordinates if for AB is this, so for A, if the coordinates is A1, A2, A3. Now this is how I will present the coordinates of a point. I will use a bracket, okay, and then 3 values inside the bracket. That'll be my coordinate information. Okay. Same thing for B. Okay, so that'll be the B. The coordinates for the B. Okay. Based on the coordinates, then you can calculate the vector AB, and you can also calculate the length of AB. So now, first of all, the vector AB, right? So the vector AB, if you calculate using the coordinates, here is the way you will write. Okay, you will write it using a so-called, I call it half angle at here. So it's a half angle. within the half angle, because this is AB, so you're going to use the coordinate of B, subtract the coordinate of A. So that'll be B1 minus A1, comma, B2 minus A2, and B3 minus A3. So that's how you can calculate the coordinate, the vector AB. So you see the difference that here? It's instead of the regular bracket, it's a half bracket I use for indication this is a vector. Okay, yeah. So and I want you to write it this way. All right. So as I said, this is not the only way in other texts, but in this class, I would like we all use this way here. So later you will learn, in terms of vector, you always have either, particularly when you use a MATLAB, whether it's a row vector or it's a column vector, right? Yeah. So there's a difference there. And in my class, I always write it as a row vector. In some other class, it always, when you mention a vector, it always means actually it's a column vector. Okay, so that would be a difference. And now you can calculate the length of this AB vector. So the length of the AB vector, the formula you learned already. So basically, you square each one of the components, add them together, and then you take a square root. So that'll be the length of this vector. Okay. So now you get a sense, how would you get the vector, how would you get the unit vector, and then we can put things together. So if I have a vector AB, then how do I express this vector? I can express it as its length time its direction. So that will be the two components of a vector, right? Length and direction. Okay. Yeah. Good. Okay. So another small thing that I've seen some people get confused is, for example, you have a point A at here with A1, A2, A3. Okay, so you have a coordinates A1, A2, A3 for the point A at here. Okay. Now, if you see a writing A, A1, A2, A3. Okay, so if you see this, okay, as a matter of fact, forgot to turn on my little pointer here. So if you see this one in here, right? From here to here, what does that mean? What is the difference between this and this? Yes?
One of them is a point A in a space. The other one is a vector from the origin of that space.
Excellent. Okay? Yeah. So this one here literally just basically means this. Okay? Yeah. And you can test it. I mean, you can use this formula. AB is this is the formula for vector AB, and literally this is OA, right? So use the coordinate of A minus the coordinates of O, and you get this one here. Does that make sense? So it's actually quite important. It's a small difference, but sometimes, okay, but it tells you completely two different stories, right? Yeah. So make sure you're able to identify the difference that is here, right? Okay. Okay, so let's keep going at it here in terms of concept. Okay. If we keep going, and we have some very typical concept, for example, vector addition and subtraction. So this is very simple. Let's see if I have a vector A, vector B, okay, yeah. If I have a vector A and a B at here, okay. So basically, if you draw the two vectors, you probably will draw the two vectors like this. You can draw it. Okay. You can draw it like this. I mean, literally, you don't have the B may not necessarily is here. It may be somewhere else, but you can always align this the initial point with the termination point for the A here, so AB. Then you can draw another vector from this initial point to the end point of the B. So then that will be basically, right, the addition A plus B. Okay. So that's simple addition. And of course, you can have a different way of drawing. Maybe if you draw it this way at here. So if this is A, this is B, then the way they present at here now, it'll be A minus B, right, for this one. So that'll be a subtraction. Okay. So that's how you use this so-called head to tail rules, okay, to do subtraction and addition. I think that's pretty straightforward. Is that good? Okay. Another small thing before we move on is let's associate basically another notation wise. We learned the notation for unit vector. So I hat, J hat, and a K hat, right? Okay. And then I presented saying, okay, so if you have a vector A at here, okay, so you can write the vector A as A1, A2, A3 like this, okay. So that's your vector OA or OA vector, A vector is fine, okay. The other way of writing the vector, so for this one here, for example, this one, okay, I can also write it like this. So A1 I hat plus A2 J hat plus A3 K hat. Okay. It's the same expression for this vector. It's just different ways of presenting it. Okay. Get used to this notation. Oftentimes I will write this interchangeably, and sometimes write this way, sometimes write that way, and just bear in mind we're talking about the same thing at here. Okay, yeah. Okay, so this is all the simple concept on the vectors at here, and then there are basically two important vector basically operations. One of them is a so-called vector dot product. Okay, and the other one is the vector cross product. So that let's see how much we can do, and then we'll get on with both of them. Okay, just quick reviews. Dot product, you use that quite a bit in statics, dynamics, and the EMAC course. So so does this cross product. Okay, so first of all, let's take a look at the definition of vector dot product. The definition of vector dot product, okay. It's basically the vector multiplication okay. It's a multiplication of two vectors, and it gives a scalar. Okay, so that's the definition. So here is the formula. Okay, let's see, we have two vectors. Okay, so A1, A2, A3. And B1, B2, B3. Okay. Then here's how you would write a vector dot product. So A dot B. Okay, so within the vector A and B, you use a solid, obviously very clear solid dot between these two vectors, indicating this is a dot product. Okay, it's not just a regular multiplication of two scalars. And then you can write it, okay, based on this information of A and B at here. Okay, you can write it as A1 times B1 plus A2 times B2 and A3 times B3. Yeah. That's how you calculate the dot product. It's very simple. I mean, you use the first one, the second one, and third one times the corresponding components, right, in the other vector. Okay? Yeah. There are different names that for dot product. Sometimes you call it inner, okay, or scalar product. Right. So you look at the results. It's a dot product, two vectors, and then it ends up with a scalar quantity, right? And you can write it in a more concise way at here. Okay. You can use a summation sign to write it in a very concise way. So we define our vectors only in a 3D. So that's why you see there are only 3 elements, right? And basically in 3 dimensions. If you're talking about general dimension, n dimensions, then you actually would have A1, A2, A3, and then up to AN. So that's also a vector. Okay? Yeah. So we'll just focus on vector with 3 elements. Okay? So that's where our focus here. And then you can easily change the 3 to any number, to n, if you have a n-dimension vector dot product. Okay? So that's the definition of dot product. All right. Yeah. As for dot product application of it, and we often use a so-called the geometrical meaning, okay, of this dot product quite a bit. Okay. And what this really means is you form your move the 2 vectors. Okay, so move them and then make sure they form an angle, okay, between these 2 vectors, okay, and then make sure their initial point align the same location. Okay. So that's a vector. You can put them together. Vector is free, right? Yeah. Then we can relate the vector and the angle theta together. Okay. So this is the geometrical, basically the formula here. So A dot B equal to this times cosine theta, right? Yeah. That's the geometrical application of the dot product here. So, or geometrical formula. So A dot B equal to this. And apparently the difference between this formula, the first formula and the second formula, is the second formula has a theta angle introduced at here. That's a new formula, right? Other than that, you look at the other side. This is a calculation of the length of A, length of B. So that's not really new. It's the angle here. Okay. And when you form 2 vectors together, okay, and obviously the angle between these 2 lines or 2 vectors, it's going to be either between 0 or pi, right? Yeah. If the A goes beyond pi, then you look at the angle the other way, right? Yeah. So instead of one direction, okay. So that's how your range of theta is, right? Now, this formula can be proved mathematically using the so-called law of cosine. This is something you learned in high school. Okay, so if you're interested, you can come to me, but we'll skip that part of the proof there. Okay. For this formula, what really most used for is you actually use it backwards. You calculate theta based on this formula here. So you can use it to calculate backwards, and then you calculate the theta by calculating the inverse cosine. Okay, so that's how you would be able to get this theta here. Okay. Now, and the other thing is when you look at the arrangement of the 2 vectors. There are some special arrangements between this A and B, and that actually tells you immediately, based on the value of A dot B. So for example, right? Yeah. Let's say if I have A dot B equal to 0. Okay. So what do? You probably calculate A dot B using this formula. Right? You got a 0. Then what does 0 mean? What does it tell you geometrically for the vector A and B? If this is a 0 value at here.
The closest theta means 0.
No. Perpendicular, meaning theta equal to 90 degree. That's right. So, right, you can base on this one. If this is 0, this whole thing is 0, then the inverse cosine, and what's the cosine? Cosine is this, right? So basically, when it's 0, it's 90 degree. So that's why this is theta is 90 degree. And theta 90 degree means A and B are perpendicular, right? Now that's a quick information you can get, okay, through this geometrical formula here. Okay, perpendicular. I sometimes often call it they are orthogonal. Okay, usually perpendicular is a concept in 2D. And when you say orthogonal, they're a concept more or less for more than 3 dimensions for 3D. So you could have an n-dimensional, 5-dimension vectors dot each other equal to 0. I mean, you can visualize that, right? So beyond 3D, you can visualize that. Only 3D, I can visualize the vector using 1, 2, 3, A1, A2, A3. But beyond that, you can't. But this perpendicular or orthogonal information still holds, right? So that's the idea of conveying this information. Okay. And then you can also tell, let's say, if A dot B happen to be greater than 0. So this quantity is greater than 0. And the bottom two quantity are naturally greater than 0. So the whole thing inside the bracket is greater than 0. Then you look at the cosine curve. Which range of theta give you a value cosine of that theta is greater than 0? It's between what? Between 0 and pi over 2, right? So that gives you an idea for theta's range. So 0 to pi over 2. Okay. And of course, if your A dot B, okay, is less than 0, then that means the theta must be between pi over 2 and the pi. Okay. Yeah. Okay, so that's the geometrically how you would be able to identify these 3 obvious informations here. Right. One of the application also through this geometrical formula here is, okay, we use that quite a bit actually. We use it for so-called vector projection. Okay, vector projection here. For example, you learned in, let's say, dynamics. You may have a acceleration, for example. Okay, you have acceleration vector pointing that way, and you might be interested is, so what is the acceleration? Decompose this acceleration in 2 different components here. Right. So let's say I call this as a perpendicular and a parallel. Right. So that's something that you might be interested to decompose a vector in 2 directions, 2 perpendicular directions. Okay. And then how are we able to obtain these 2 direction, the other 2 components of this guy here, right? So how do we do that? We're going to do this. We can do that using the so-called vector projection. Okay, yeah. So I'll use an example here to illustrate this idea here. Okay, yeah. So let's say here is a vector B, and here is vector A. Okay, yeah. And I'm really interested in this. I wanted to know if I project this vector A onto the direction given by vector B. So project, right? Project basically means is you look at the perpendicular in that direction. You learned in the CAD drawing, and then look at the shadow of this one right here. Okay, so that will be your projection, right? Yeah. So maybe the 2 vectors have an angle theta in between. Okay. So then, if I do the projection, I got basically a vector, a new vector at here. Okay, right? So from here to here, that's a new vector. So I'll call this vector, let's say, A parallel. Okay? A parallel. Good. So the idea is, what will be this A parallel at here? How do we calculate this A parallel? Okay, what will be a formula for doing this, calculating this A parallel? Cool. Okay. So let's try this, right? Here's what I would write. So I write A parallel, and I'll shorten it. I'll say A parallel is a projection of vector A, okay, onto the direction of B. Okay, onto the direction given by B. Okay, so that's a shortened description for this problem right here. Cool? Yeah. Okay, so we're gonna actually go back to the simple concept for the vector. Now, can you remind me what's the two components for a vector?
Magnitude and unit vector.
Good, right? So magnitude and unit vector. So apply the same concept here. If I want to find out this vector A parallel, I need to find out its length, and I need to find out its what? Direction. Okay? So I'll just use maybe two brackets at here, indicate these are the two things I want to fill out the blanket here. Okay? So let's find the obvious one, direction. Apparently, the direction of A is in the same direction of what? The B, right? Okay? Now, back to my simple concept before. What do we use to indicate the direction for a vector? I heard it. Unit vector, right? I use unit vector to indicate the direction. So here's a B. So what's the B's unit vector? It's what? B divided by its length. Okay? Yeah. Does that make sense? Okay. Then let's get back to this bracket here, the length. So length may not be as obvious as it is, but let's come back to this drawing right here. Okay, to this drawing. Now, if you look at this drawing, and if you the first thing jump to your mind maybe would be what you learned in high school, right? Let's see if I ask the same question as a high school geometry problem here. So what you see here is you see a right triangle here, isn't it, right? And then this triangle, you have this hypotenuse here, and then you have this vertical side here. And if people say, you know theta, you know this length, I want you to calculate this length. Is that doable, right? Okay. So what's this length of this side here? It's given by this vector, isn't it, right? What's this length? It's this guy. How do I calculate the length on this side, you know? Yeah, cosine, right? There we go. Yeah. So that's how you put things together. This is the length times direction. Okay. Yeah. But the tricky thing is you got a mixture of a theta and an A and a B, so that doesn't look very pretty. We want to be consistent. Maybe we wanted to have a formula that deals with only A and a B, right? Yeah, because this is the given information A and B. So we want to get rid of the cosine theta. How do I get rid of the cosine theta? We have, yeah, go ahead.
A dot B divided by the magnitudes of both multiplied together.
Exactly, right? We just covered that simple geometrical formula. Okay, so let's just replace this cosine theta with the formula that we just presented here. Good. Yeah. Yeah, thank you. Sorry, what's your name again?
David.
David, yeah. Yeah, this is how I can try to remember people's name actually. So this is how we after the replacement, and that's what you would have here, right? Okay. So now you see there's a whole bunch of A and B's here. Okay, it seems to be pretty messy. But now we actually will be able to do some cancellations, simplifications here. Is that good? Okay. So let's do some simplifications here. Okay. So look into the bracket here. You have A here. You have A here. Well, that cancel, right? Two scalars. You can cancel each other. Okay. And then probably nothing too much we can do now. So this is basically the only cancellation you can do. Okay. However, okay, I can still try to shorten this expression a little bit here. So I can look at it this way. Here's B over its magnitude. Here's also what? B over its magnitude. And what's the symbol we use for the vector over its magnitude? This is what? B hat, right? And what's the symbol for this one here? B hat. And then we keep the A at here. So A dot B hat times B hat. And that's the solution at here. Okay, so after going around the clock, we got an expression for the projection A parallel, which equal to this. Is that good? Okay. Let's examine this formula again before we call it off for today. Okay. So let's look at this final result set here. Now, I want you bearing in mind of the simple concept of vector. What is the geometrical meaning for the quantity between this bracket? Vector equal to what times what? Length times direction. So what's between this bracket? What's this guy here, first of all? Direction. Then what's this one? The length, right? So A dot B hat is the length of this A parallel. Basically, I can conclude that A dot B hat, right, is the projected length of A parallel. Does that make sense? Okay. Now this actually, I want you to memorize one thing now. When you use a vector dot a unit vector, what do you get? You get a scalar, of course, but physically, what do you get? Geometrically, you get what? Projected length. Okay? Yeah. So basically, if I have an A vector, a B vector, and somebody asks you, can you find me the projected length of this vector in the other direction? What do? You use this vector dot the unit vector in that direction. That's it. Okay? Yeah. So we'll continue from here to the next week. Next week. Okay? Yeah. Thank you.